Okay, it's an honor to be in this meeting for Agu's birthday, and I would like to thank the organizers, Yao and Paul, for the invitation. I'm sorry for those of you who already heard this talk, and also because it might be difficult to read, I realize now. So the main topic of this talk is the understanding of the KPZ, the appearance of the KPZ universality class in undirected models. This means models where it is possible to revisit several times some sites or some positions. So, well, I will start giving some context about what's known for directed models, especially polymers and random walks. And I will explain some known results, especially in the case of the directed models. Then I will introduce the planar stochastic heat equation. And finally, I hope to be able to state the main results, especially the existence theorem, I hope to be able to explain the construction of what's called the polymer measure. And finally, I will give some ideas of the proof if I have time. So what I'm here, let's see. Okay, that's better, maybe. I don't know why it's 2 pages at once, okay. So, okay. So there are 2 models which motivated my work with Jeremy Quastel and Balin Virag. So this is a joint work with Jeremy Quastel and Balin Virag. I didn't mention that. One is the model of directed polymers. So as you can see here in this picture, I hope you can see it. We're looking at directed paths, upright, leftward paths, which accumulate weights, and the weights are defined in space-time. These are the omega and x, and one important quantity here is the point-to-point partition function. So you sum over all the paths going from 0, 0 to nx, and each path will have a weight given by the product of the weights or the corresponding vertices. So this model has something that is most of you know, which is called the weak-strong disorder phase transition, which can be seen happening in dimensions larger than or equal to 3. So in this picture, the vertical axis would correspond to dimension 1, but I could have made it, or I could have define this in any dimension, in any space dimension, and this is a well-known phase transition of this model. Then a model which was very important, a very important motivation, I would say, especially, at least for me, in this work, is the random walk and random environment model. So I think this random walk and random environment model is it's not so different in the end to the polymer model, maybe not directed, but let's look at this picture here. The random walk and random environment model is simply a model for a random walk which in this context, which jumps to nearest neighbors. So from 0, 0, I can jump to in this picture to these 4 nearest neighbors, and the jump probabilities are random. So, and I will consider at some point even non-directed trajectories, which means that the random walk can come back to the same vertex several times. So what corresponds to the point-to-point partition function is the end-step transition probability, which is written here. And as you can see, it is it has a similar, let's say, it looks similar to the point-to-point partition function, and actually the models will turn out to have an important, there's an important analogy between them, given by the fact that the random walk and random environment model also has some phase transition, which corresponds to the weak-strong disordered phase transition. In the case of the random walk and random environment model, this phase transition is expressed in terms of the equality or non-equality of the large deviation rate functions. So there was a work of Attila, 2011, 2010 also. Attila had a work for the random walk on space-time IAD environment, where he showed that under some above certain dimensions, the annealed or average rate function is equal to the quenched one. And more recently, in collaboration with Rodrigo Asais and Chiranjeev, and Santiago Sagletti, so Sagletti here, we showed that there is a quantity analogous to the temperature, for which shows that there is a phase transition in terms of the equality and non-equality of the rate functions. I'm not going to talk more about that. This is just to illustrate the fact that these two models I consider that have similar futures. Now, and it turns out that also there are two special cases for both models, which are, sometimes people call them exactly solvable. I will begin describing the random polymer model, the directed random polymer model. So for a special choice of weights, which is called the log gamma polymer, again, I think most of you know this, it is possible to show that the fluctuations around the log of the point-to-point partition function scale like into the 1/3, and the limit is the Tracy-Whittem GOE distribution. So this was proved by, this was proven by Cepalainen in 2010, and then extended by Borodin, Corbin, and Remenick in 2014. And there's a similar solvable case for the random walk and random environment, which is called the beta random walk. So the beta random walk is a random walk where the jump probabilities are given by a beta random variable. And I should say that the original definition of the model is in space-time IAD environment. So the probability to jump to the right is given by the beta random variable, and the probability to jump to the left is 1 minus the beta random variable. So this model is also exactly solvable. And so here's the a diagram of what I explained. the probability of jumping to the right is the beta random variable, which depends on two parameters, alpha and beta. And to the left, which in this picture is downwards, is 1 minus b. So in this case, I'm not going to, I think I'm not going to define all these quantities here, but in this case, there is a corresponding fluctuation theorem for around the quenched large deviations of the random walk. So here the I sub q is the quenched large deviation rate function. Theta is a parameterization of the endpoint. And again, it is possible to show that the log of the point-to-point transition functions has fluctuations of the order n to the 1/3, which converge to the Tracy-Whittem GOE distribution. So this model was introduced by Corwin and Varadhan in 2017, and they proved this theorem for alpha equals beta equals 1. This was extended for arbitrary beta in 2021 by Korochik. And a couple of years ago, in collaboration with Oviedo and Gonzalo Panizo, we extended it for arbitrary alpha and beta. There's some restriction of the theta. I'm not going to, again, enter into this detail. Okay, now, it turns out that for general models of directed polymers or random walk in random environment, there is a method, a very nice method introduced by Tom Alberts, Kostya Kanin, and Jeremy Quastel in 2014, which gives rise to the KPZ equation at the level of fluctuations. So I want to explain this in the context of random walk in random environment. So if I choose, if I look at a random walk in random environment where the jump probabilities are perturbations around the simple symmetric random walk, so that's why there's, if you don't see, there's a 1/2 here, 1/2 plus something small, which is random, and so in this case, I'm looking at a model, at a case where the probability of jumping to the right is 1/2 plus square root of epsilon psi, and to the left is 1/2 minus the same quantity. Then it turns out that if I look at the transition probabilities of the random walk, where time is rescaled like 1 over epsilon squared, epsilon is a parameter which will go to 0, and space like 1 over epsilon, one component of space like 1 over epsilon, and the other one like 1 over epsilon squared. Well, it's a special endpoint. Then these transition probabilities, when I renormalize them appropriately, converge in distribution to the solution of the stochastic heat equation in dimension 1. So this is the one-dimensional stochastic heat equation where psi is space-time white noise. And it is important to understand that this equation is connected to the famous KPZ equation through the Hopf-Kohl or Kohl-Hopf transform. So this is a. So V is just a parameter which is it is parameterizing the endpoint, as you see here. But the important thing is that this result is valid for any random walk and random environment, or also directed polymer as originally done here, for which the disorder is locally small. Okay. Now, as I said, the main question that I want to address in this talk is how to observe or the appearance of the KPZ universality class in undirected models. So I will to be more precise, I will explain how we were able to show the appearance of the KPZ equation, which is exactly, or through the 1 + 1 stochastic heat equation for undirected models. The original motivation from my side was trying to prove this for random walks in random environment, not necessarily directed, which is not what I will present actually. So there are a few results in this direction. I want to mention one of Agarwal Wang in 2021. But today I will focus on on a model which is called the planar stochastic heat equation. So I want to emphasize something here. So the planar stochastic heat equation is a heat equation in dimension 2, not dimension 1. So this is 2 + 1. It's different from the previous equation I showed you. And the noise is only spatial white noise. Does not depend on time. So this can be seen as an equation corresponding to a random polymer in a random polymer which is not directed, but partially because of the fact that the noise is not space-time, but it is a spatial white noise only. So, okay, this is the model I will study here. Let me start giving you some background about this model. So there are a couple of works of Nualart Sakai and Yao Zhong Hu of 2001, where Hu studied this equation through a chaos series expansion. But actually, the chaos series expansion, he showed that this chaos series expansion converges only up to a critical time in L2. And after this critical time, the L2 norm blows up, and the expansion does not converge. Well, let me skip this part. It doesn't matter exactly what this critical time is. But I should also say that there's also several works, but I didn't write them here. I want to mention especially one of Heider Labe, where they are able to prove the existence and uniqueness of solutions of this equation, but their solution is not is a solution which is different from the solution of Hu. There are different objects in a sense, And the difference between these solutions depends on the way that the way in which the approximating objects are renormalized. So this is something that is that I think I will explain in what follows. So let's see. So the solution of Hu, which I quoted here, I will call it the weak order solution. Let's look here at some kind of formal definition of the solution of this equation. If you use naively the Feynman-Katz formula and use some symmetries, you can see that it should be possible to express it like this, or more or less. So this is these two points are some notation some people use to say that, well, really I cannot take the expectation of e to the, it says here, integral from 0 to t of psi of bs. I cannot just compute this expectation because it's going to blow up. By the way, this q, which will appear several times in what follows, is a Brownian bridge between 0 and x at time t. Okay. So, so the thing is that essentially you have to think that when I write this exponential, I am really writing exponential of the integral from 0 to t of psi minus something, and this minus something is what I call the renormalization. There is a limiting procedure behind this. So I cannot write here, but I want to say that in the case of the weak order solutions, the quantity that is going to be subtracted in the exponential is going to be 1/2 of the variance of this exponent with respect to the randomness of the noise. So I think I cannot use this to write, but okay. So let me give a more formal definition of this weak order solution. So in what follows, I will say that a function u, or is a weak order solution of the planar stochastic heat equation. If I can express this function u as using Duhamel's formula, essentially, as an integral where the spatial integrals are Skorohod integrals. And the reason why the Skorohod integral has to be used is because the integrand in general is not going to be adapted. So you cannot just, and it turns out that this representation or this definition coincides with the definition of Hu up to the critical time. It corresponds to this chaos expansion. So the first result I want to give here is the following one.
Sorry, if you come back to
yeah.
this definition of Skorohod, if you take this, you can see directly on that there was a time where it blows up.
No. It's not obvious. But the fact that there is a time, I mean, you can see it a little bit formally from here because so as I said, I have to subtract here something. But if the L2 norm of this quantity ends up being can be expressed as an expectation of e to the power of a mutual intersection local time, and this mutual intersection local time is known to blow up at this time. So you can see it like more or less like that, but it's not a difficult computation, by the way. So okay, now so the first result I want to give here is a result giving existence and uniqueness of a weak order solution for the planar stochastic heat equation. So there is a way of, and also in this theorem, we showed a way of constructing the solution as a limit of martingales. So maybe to state it, let me say the following thing. An expansion in terms of orthonormals, I will first choose an orthonormal basis of bounded functions, and then I will expand white noise using these orthonormal functions. So these psi j's are going to be IAD. So it turns out that this series I am writing here, the sum from I equals 0 to n of psi I mi minus 1/2 mi squared, where mi is the integral over the ith member of the basis evaluated at Brownian motion at time s. So it turns out that formally, if this series I add it up to infinity, this is going to be exactly the expansion of this integral minus its normalization. So I am just truncating the expansion and take the limit. So the important fact is that these martingales are uniformly integrable, and they converge in L1. And the limit is a solution of the planar stochastic heat equation, but beyond the critical time. The solution that we obtain is valid not only up to the critical time, but also beyond the critical time. Okay, so so let me see. I said this stuff already. And the second result that we obtained with Jeremy and Valent is actually an intermediate disorder result.
So the limit of this thing is the solution?
Yes.
Even after the
critical time.
It's in L1, but not in L2.
Exactly.
Oh, I see. So it blows up in L2, but
not in L1, exactly. So the second result is the following. Given a solution of the planar stochastic heat equation, I'm going to look at a family of solutions parametrized by several white noises parameterized by this quantity n. So the psi n is a rescaled white noise, which turns out to be a white noise which has the same law as the original one. So this is invariant in law in n. So it's just a way of writing it. So it turns out that if I look at the solution of this equation at large times and at large vertical coordinates, so you see there's an n here, there's an n to the 3/2 multiplying time, and and there's a diffusive scaling in the horizontal coordinate. Then this converges again to the solution of the 1+1 stochastic heat equation with some normalization factor. So this is exactly the type of result I already quoted in the case of random walk and random environment. The converges, I think I say here, it's an L1 again. Okay. So I think I have some minutes to explain the connection between these results and the result of Heider-Labé. So Heider-Labé have a result, as I mentioned, they have an existence result for the planar stochastic equation, which actually they call it the PAM equation. So maybe to fix vocabulary, I'm going to call their solution the PAM solution and this solution the weak order solution. I should mention a couple of things. The weak order solution is not does not satisfy the semi-group property. So it's not, in that sense, it's not maybe so physical. But it has some interesting qualities, and the PAM solution does. But there is a connection between them, which I want to explain. There's a way of going from one to the other one. And that can be, so I actually, it is possible to express, essentially, it is possible to express the PAM solution probabilistically in terms of the weak order solution. So let me give you some, a little bit of, I have to define a couple of things to do this. So first I need to define, at least formally, what I will call the polymer measure. So the polymer measure is a measure which is weighted by this exponential, which was so important in the definition of the weak order solution. You see the same exponential here. I'm writing it for the polymer measure. So I'm weighting all the paths by this series. Here it's infinite, doesn't matter. It's formal what I'm explaining. Yes?
Can you say that the Heider-Labé solution, is it global or is it also local?
It's global.
It's global.
Yeah. You mean in time?
In time.
Yeah, sure. Yeah.
It's application of regularity structures, but nonetheless it's global in time.
Sorry?
It's application of regularity structures. I don't know, but as far as I know.
No, but actually the way they prove it is more elementary than regularity structures.
Okay.
Yes. It's,
That's why I was looking. That thing works only.
it's a change of variable argument. It's not okay. So this is the formal definition of the polymer measure, which actually we can construct using our methods. So maybe let's skip this. But now, using the polymer measure, it turns out that the PAM solution, which is the solution of Heider-Labé, can be expressed as this expectation under the polymer measure. So this might look maybe it looks a little bit mysterious, but it's not so difficult to understand if I try to see the differences between the renormalization of the PAM solution versus the renormalization of the weak order solution. So the expectation is of e to the gamma, where gamma is the self-intersection local time of a Brownian bridge. And there's an extra constant, depending on time, that you have to add out here. But this self-intersection local time can be expressed as this series. And actually, this series is the difference between the first series is the renormalization that is done in the case of the weak order solution, and the second one is more or less the renormalization you would expect that Heidel did, because in their case, the renormalization is not random. So, okay, I think I was going to explain a little bit some of the ideas of the proof, but I think I don't have time, so thank you very much.